So welcome. So this is the first lecture in our section on oscillations and waves. 4 chapters. This is the first chapter, and this is on oscillatory motion. And what we're going to talk about? We're going to talk about specifically simple harmonic motion. Not all oscillations are simple harmonic. The simple harmonic oscillations are ones that tend to have, they have a system that obeys Hooke's law. So if you think back about springs, classic simple harmonic motion. A spring will give you simple harmonic oscillations. Some other systems won't. And so we're talking about one set of systems, but it turns out it's a very common set of systems. So we're going to talk about simple harmonic motion. We're going to play games with it. We're going to turn around and say, well, we know a few laws about springs and forces, so we're going to see what we can learn. So the first thing we're going to learn is that we can derive a relationship between acceleration and displacement pretty easily. We're going to basically realize that with a bit of trig, we can derive a relationship between displacement and time for our simple harmonic oscillator pretty easily. And we can actually even do velocity at any given instant pretty easily. And we can do acceleration at any given instant pretty easily. So this is kind of fine. We're looking at an oscillator and we can stop the film and we can say, oh, look, let's measure its displacement. Let's measure its velocity. Let's measure its acceleration. And we get good numbers. And then we say, well, gee, I wonder what determines why some things oscillate at a high frequency and some things oscillate at a low frequency. So we'll find out what matters and what doesn't matter. And then we're going to do some more playing. So all of this so far has been really important. And then I'd say this is a smidge less important. What I kind of mean by that is all the equations so far I expect you to have in your head. No equation sheets for this course. Okay? You've got to remember these things. I mean, I expect my singers to know the words to their song. I expect my high school teachers, I know they have to know the equations. I expect my doctor to know the names of the drugs. I expect my engineers to know the equations that they're going to use. So you got to know these equations. But there are some equations where at some point I've got to draw a line. And so there's some equations where I turn around to you and say, well, you don't need to know this equation, but if I show you the equation, you've got to be able to use it. So I might give you one of these more complicated equations and say, oh, by the way, this is the equation. Now, how would you do this with it? So you can't just like write it off and not have a clue what it stands for. You've got to understand it. And that's what we're going to do here. We're going to talk about instantaneous kinetic energy and instantaneous potential energy. And then the total mechanical energy, I expect you to know. It's pretty straightforward. And then we're going to do sort of more practical, kind of interesting stuff, which unfortunately... Oh, no, sorry, wrong line. Then we do more practical, interesting stuff, which unfortunately involves math that you need not have. You don't have to have differential equations by this course, and most people don't. And to get the answers that they get, they pull it out of a hat, and they go, oh, look, and here's the answer. And I'm never that comfortable when they do that. I'm not going to make you do the differential equations. It's just like we're going to be a bit more conceptual at that point. And if you have done differential equations, you can look at it and go, oh, that's great, but I'm not going to ask you a question about doing the differential equations on it. So you get a bit of a previewing of what differential equations are useful for, but you're not held accountable for that. So we'll talk about damping and resonance. Okay, so this is my visualization. I find most students limit themselves because they don't think this course involves drawing diagrams. And so they immediately go to sometimes numbers, or they go to an equation and then numbers. And because they're not drawing diagrams, they misinterpret the question. So they'll get signs wrong. They'll get, sometimes, rather than adding something, they'll subtract it. And so they get the answers wrong. If you get the wrong direction, it's wrong. If you want to drive to Orlando and you head down to Miami, it's not right. You know, you might have driven the right distance, but you're in completely the wrong place. So the signs do matter. Okay, so we need a diagram and we need a visualization. And my visualization is of a spring on a horizontal table that's frictionless. Why? Because it's nice and symmetrical. The oscillation is horizontal. And if I do what I'm showing you here, and sometimes I will talk about it, but if I do a spring with a mass on it, sometimes people get concerned about the symmetry. After all, there's a force acting downwards but not upwards. Well, there is a different force acting upwards. But they kind of feel like, man, is it going to be a symmetrical oscillation, or is it going to be more downwards than upwards? It turns out it's not. But to keep things simple, we'll just visualize, unless we're told otherwise, a horizontal table with a nice spring on it, massless spring, and a mass on the end of it. And it sort of rests on the table. It's not like one of these springs where, you know, I can't squish this spring. It runs into itself. It's such a weak spring that metal touches metal. Imagine a car spring. You can't push a car spring so that metal touches metal. It's such a stiff spring that it's really hard to compress, just like it's really hard to expand. So we think about that kind of spring. And what happens is we have a nice equilibrium position. To make the math simpler to begin with, I'm always going to move the mass to the right and then let it go when the clock equals 0. In real life, you don't have to do that, but to make life simple to begin with, we're always going to move the block to the right-hand side and then let it go when the clock equals 0. We're not going to push it. We're not going to delay it. We're not going to move it to the left. We're going to move it to the right and then let it go when the clock equals 0. And what that does is that determines the amplitude of my oscillation because I let it go. So that's as far as it's going to be away from equilibrium, and it's going to go back to equilibrium, and it's going to be a nice. So now I'm envisaging this. We have a nice symmetrical system where I moved it to the right and let it go. So there's my amplitude. This is time, of course, going downwards. So okay, that's kind of nice. And because I let it go when the clock said 0, this is 0 seconds, and time goes down like that. So, nice. Okay, so I say an object moves with simple harmonic motion whenever its acceleration is proportional to its displacement from some equilibrium position and is oppositely directed. Oh yeah, what that means, where's my pen? What that means is it's Hooke's law. And Hooke's law says the restoring force is equal to minus kx. That's what Hooke's law says. We did that in Physics 1, Hooke's law. If it obeys Hooke's law, then it follows a thing called simple harmonic motion. I need to put my glasses on because I can't see my pen if I'm not careful. So it's simple harmonic motion. And we consider a block attached to the end of a massless spring. The mass is in the block, it's not in the spring. As far as we're concerned, the block can slide horizontally across a smooth horizontal table. So here's my picture. When I displace my spring end to the right, the restoring force is to the left. And when I displace my spring end to the left, the restoring force is to the right. Most common mistake on this is people think about the applied force, not the restoring force. But Hooke's law is about the force in the spring, not the force applied to the spring. So we've got to be careful about our directions here. And how do I represent that? If I drew it as a graph, I would have force versus position. And what I'd find is that I had a graph that kind of looked like that. When I have a negative displacement, when I'm over here, I have a positive force, and when I have a positive displacement, I have a negative force. So it's a negatively sloping line. If it's a stiff spring, it looks more like that. If it's a weak spring, it looks more like that. But it's a line which looks like that. Okay, and I can say, well, I know that the expression for Hooke's law is F is equal, well, FR is equal to minus KX. Own the equations. You cannot use wacky symbols. You can't say, oh, I like Greek letters, so I'm going to say epsilon equals something, something, because I know what I mean. Because that's fine. You know what you mean. I'm not going to give you any points for it. So you can't change the symbol just willy-nilly. But you can own them to the extent that this is a restoring force, so put down FR for restoring force to remind you that this is a restoring force. If you put F, it could be any force. Call it the restoring force. So the book will say F, but you put FR in it. And sometimes we have a whole bunch of different Ks or Bs or... So if you tend to get them confused, you might have one of them be a little K, another one could be a little K with little symbols on, and just do what you can to make it that you understand the equations really well. So own them. You can't make them, obscure to other people, but you can tailor them to be your own. So the restoring force equals minus kx, where x is your distance from your equilibrium, and k is a spring constant depending upon the spring. Can you tell me what units, just looking at that graph, that equation, what units must k have? Just rearrange that equation and tell me what units k must have. It's going to be newtons divided by meters. So my K is going to be in newtons per meter. And that's, so I can get used to that. Just rearrange things and it all makes sense. Try not to have equations be that magic box over there that kind of gets me the answer. And try and make it something that you've internalized. It's just a shorthand way of saying a relationship. It's like it's something that you live with it and you get very comfortable with. And then the next thing is, well, we also know that this thing must obey Newton's law, Newton's second law, so F is equal to ma. Well, you know what? These forces are the same. So that means that minus kx is equal to ma. So A is equal to minus k over m times x. Whoa, I just invented an equation. I got a relationship that was not obvious to me by taking two obvious relationships and combining them. And that's what progress is. That's what engineers do all the time. That's what scientists do all the time. And it has insightful bits. So let's just be a bit insightful with it. If I have a massive mass, it means my acceleration at any particular position will be less, yeah? If k stays the same and x is the same, but I increase my mass, I'm getting less a. So as I add mass to the system, it's becoming less accelerating at any point, which means it's more sluggish. And that's kind of what I saw, isn't it? Yeah. And if I was to switch out a weak spring for a stiff spring, at any given point, I would get more acceleration. So it would be more oscillatory. We saw that. So when you get an equation, especially a new equation, interrogate it and say, what are you about? What are you telling me? Do you make sense? And it stops being this magic formula. It starts being something where it's just expressing what you kind of know. So always try and go back to a physical reality with the equations. Cool. So we invented an equation. I don't remember that equation. It's one of those ones where I don't remember it because I know that really well. I know that really well. I can get that any time I like. So I know it. I just put it as a two-step problem rather than a one-step problem. But if you want, you can learn it. If you want, you can learn that equation. It's just, it's the material that's accessible to us. It's just, how does it go? In a simple harmonic system, is acceleration constant for different displacements? So what am I doing first of all? Well, let's change the color of my pen so you can see this a bit better. So in a simple harmonic system, so what that says to me is, there's my simple harmonic system. and this is my position, and this is time. And it says, is acceleration constant for different displacements? Oh, I kind of need an expression between acceleration and displacement. Oh, I remember. F is equal to minus kx. F is equal to ma. Put the two of them together. Minus kx is equal to ma. Oh, I remember. A is equal to minus k over m times x. So everything else kept constant. Is A constant if I change x? No, if everything else is held constant, call it 1. Call k over m1 to make life easier. If I change x, I clearly change A. So, okay, that is never, no, nada. You know, it's not going to happen. There's a repeat, so I'm not talking about that. I'm talking about as you change x. Not as you come back to the same x, but as you change x. Cool. So that was something where I think conceptually we couldn't have answered that question 5 minutes ago, but now we can because we're interrogating an equation. What kind of relationship links acceleration and displacement? Oh, so that's just asking me for this bit. If A is equal to minus k over m times x, is a tip. Put your y-axis in a box and put your x-axis in a box and then say, what kind of relationship is that? It's linear, isn't it? It's linear because you say y is equal to mx plus b, and this is a constant, and k is a constant, and m is a constant for any given situation. So that would be linear. And then in simple harmonic system, is acceleration constant for different times? I want you to do that one. So I'm going to click on this. And we're going to see. So I asked you if acceleration was constant for different displacements. But now I'm asking you if acceleration is constant for different times. So you get this thing oscillating. Is acceleration constant for different times? So you got a choice of yes, no, or sometimes. Sometimes it's like, you know, hey, come on, you know. So what is it? So think about it. 12 people go in. I've got 21 people. I've got about 2/3 through it. If you're not going to do it, if you're not going to play, just click in E. So, right, then at least I know I'm not waiting for you. But if you're thinking about it, then I'll wait a bit longer. It's going to be interesting. It's going to be interesting. What's it going to be? So you just you turn it on and then you click, you know, whatever letter you like. Almost there, a couple more people. I'm going to go until 2 minutes. Oh, come on, number 21. You can do it. Come on. Here we go. Here we go. Here we go. Here we go. Okay, stop. Let's see what people said. Ooh. It's kind of somewhat divided. Some people are saying yes and some people are saying no. The correct answer is no. The reason it's no is from this graph here. Can you see? You're comfortable with the idea that if you go to different positions, you have different accelerations, yeah? Doesn't this graph tell you that you're at different positions at different times? Isn't time continually moving on as you can't be at the same time at different positions. And so different positions are accessed at different times. So if you have different accelerations at different positions, you must have accelerations at different times, because at different times you're at different positions. Does that make sense? So the answer would be no on that one. Can you see how there was no equation for that? There was visualization for that. And so you can't just rely upon, I know some equations, I'm good at math, I'm going to get through. Because you might do really good math on completely the wrong problem. And you'll miss things. So, like sports people, if you're really good at serving in tennis, but you're lousy at whatever that is, I don't know, volleying or something, then your coach is going to tell you, you need to practice volleying. Serving, you're not going to get much better at serving. You're already pretty good, but you need to get better at volleying. You'll get more bang for your buck by improving what you're weakest at. And the same goes for physics. If you're really good at math but lousy at visualizing, just practice visualizing. If you're good visualizing but you're not so good at math, practice math. And it'll pay dividends. I was much better visualizer than I was a mathematician, and I kept trying to make my visualization stronger and surviving with my math. It was a real shame. I shouldn't have done it. Okay, so we had a little bit of a play. There's this interesting thing, which if I take an oscillator and I set it into motion, there's a curious thing happens. I'm going to show it horizontally on the board rather than vertically, but if I take my mass on a spring on a horizontal table and I watch it go backwards and forwards, it's going to be here at one point and here at another point. It kind of goes here and then it kind of goes relatively slowly, and then quite quickly, and then relatively slowly. So I see that it kind of bunches up at the extremes. Yeah, you can kind of see it's not very long in the middle, but it kind of slows down at the extremes. And if I plot this on time, what I see is, well, that's 0, and then that's after a certain time, 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 and then that's after a certain time. And what I see is I get a curve that looks like that. I get, and if I draw enough of them, I get the sine curve, like the cosine curve like that. It turns out that if I draw a circle and I basically just imagine a point moving at a uniform rate around that circle, then it turns out that my x component, so here's time t, my x component is the same as, so here's t0 and here's t1. Here's t0 and here's t1. And then here's t2 and here's t2 and so on. What I find is that the horizontal position of my circular motion perfectly matches the position of my simple harmonic oscillator. It's just amazing. It's really useful. And so we can make a link between simple harmonic motion and uniform circular motion. And we did uniform circular motion in Physics 1. So I can make this link. And here I'm showing a diagram with a whole bunch of stuff on it, because this is what we're going to do. We're going to imagine that we have a constant velocity, because that's what uniform circular motion is. So we have this thing going round and round in a circle at a constant speed. We start off when the clock says 0, and then at a certain time t, we've made it round to there. And this x component of your displacement from the middle of the circle is the same as the simple harmonic oscillator would have at that time. If you were to look at these, they're in line with each other at all points. So I can use the math of a circular motion to give me the answer for simple harmonic motion. All I've got to do is I've got to imagine a position, a tangential velocity, and a centripetal acceleration. The x component of my position is my position for the simple harmonic motion. The x component of my tangential velocity is the velocity of my oscillator. The x component of my acceleration is the acceleration for my oscillator. It's beautiful. It works so nicely. There's a little video, and I'll dig it out and put it up online so you can see it, and it's just perfect. You get the two lined up, and it's perfect. Yeah, you've got to have the right natural frequency for your oscillator, for the right size of circle. You've got to have the right speed, but you get them matched, and they're perfect. So that's the game we're going to play. Now, most of these symbols are reasonable. I kind of wish they'd put delta x because displacement usually is delta x, but I can live with that position, whatever. Vt, tangential velocity. AC, centripetal acceleration. Omega t. What on earth is omega t? We normally use theta for our angles, and theta basically most often in our past has meant degrees. We did introduce this idea about the radian, and I suspect, like me as a student, you were uncomfortable with the radian. It's not a hard concept, it's actually a very fundamental concept. It's just it's very unfamiliar. And so it's really worthwhile. Mathematically, this stuff is not going to be hard, but it's going to be very unfamiliar. So it's really worthwhile spending a little bit of time and reminding ourselves that if that's S, and that's our radius, theta, we said that the angle in radians, if you like theta rad, is equal to S over R. And from that we recognize that, the arc length, the distance around the edge, was equal to theta r. I better do that again. Theta rad times r. Angular. The angular bit as the r on the end. Okay. And, well, then we went on and said, well, if we take the change of the radians, the change of the angle in time, we have a thing called omega, which is angular velocity, which is in radians per second. And then we had, well, if we take our rate of change of our angular speed, angular velocity in time, we have alpha, which is in radians per second squared. So pretty soon you have, well, x is like theta, delta x is like delta theta, v is like omega, and a is like alpha. And how do I convert between one and the other? I go, well, let's have a look. I can say delta x is equal to delta, I can say x is equal to theta r. I can say that v is equal to omega r. I can say that a is equal to alpha r in my conversions. We did that in physics 1. Okay, so I want to talk about angles, but the angle changes in time. It's like I want to talk about position, but my position changes in time. Oh, I know what to do. I'll take my speed and I'll multiply it by my duration. How far am I going to be away from here in 20 minutes? Take my speed and multiply it by a third of an hour. 50 miles an hour times a third of an hour, I know how far I am away. Yeah. So I'm doing the same thing. I can define an angle by the angular velocity times the time. Yeah. As long as you start off at 0. 0 time. So rather than having theta, I'm going to choose to put down omega t. So there's two things going on that are a little bit uncomfortable. First of all, I'm using an omega, which is angular stuff. And then I'm not talking about theta even, I'm talking about omega t. Angular velocity times time gives me an angle. So again, it's not mathematically hard, but very uncomfortable. By the way, when we talk about this stuff, we use it as a frequency, so we actually talk about omega not as angular velocity anymore, but in this context we talk about it as an angular frequency. Because I can represent how quickly something oscillates, or how often it oscillates per second by an omega value. Yeah.
That last equation on the end there is radians over S.
It's not an equation really. It's just saying that alpha is in.
Alpha is radians over.
It's radians per second squared. Like
Squared.
acceleration would be meters per second squared. Then angular acceleration is radians per second squared. Yeah. Analogies are really useful. Throughout physics too, we're going to be doing analogy after analogy after analogy. Because you know stuff, and all you're doing is you're changing how it's represented. So it's really useful. Let's play this little bit with this. Let's have a look. An object displays uniform circular motion. It has an angular velocity, so my omega is equal to 6 radians per second. And how long does it take? So I want my delta t equals, I don't know, to revolve by 30 seconds. Delta theta is equal to 30 radians, 30 rad. So I have this situation where I have this, and it's going round at a certain rate, omega, and I have a certain delta t. I want to know where on here I am. You know, that's kind of what I want. I want to know what that angle is. Also, I want to know how long it takes to get to that angle. So I know I'm going at a certain speed. I know I have a certain angle. How long does it take to get to that angle? Well, if this was linear, frankly, what I'd say, oh yeah, let's have a look. I'd say my velocity is equal to my displacement divided by my time interval. Remember that from the very beginning of Physics 1? Yeah? And that would say that my time interval was equal to my displacement over my velocity. Yeah? Let's just think about that. How long will it take you to go 100 miles at 50 miles an hour? 2 hours. How long will it take you to go 170 miles at 10 miles an hour? Okay? So, it's as easy as that. But what we say is omega is equal to d theta by dt. So dt is equal to d theta over omega, which equals, let's have a look. My revolve through 30 radians, 6 radians per second, 6, which equals 5 seconds. It's easy, but it's not easy if you're kind of cornered by the unfamiliarity with what things stand for. If it was in miles per hour and miles, you'd be insulted by me asking you it. I'm just changing the context. It's the same relationship. And there's a big lesson there about, don't spend all your time trying to do the hardest problems and not get familiar with the simpler stuff, You kind of like, make sure you know the simple stuff. And the harder problems are not so hard then. An object displays uniform circular motion. It has an angular velocity of, so let's have a look. An object displays uniform motion. Angular velocity, omega, is equal to 4 radians per second. How long does it take, delta t, to revolve through delta theta, so it's a displacement, 120 radians. Let's have a look. V is equal to delta x over delta t, so delta t is equal to delta x over v. So that means that omega is equal to delta theta over delta t. So delta t is equal to delta theta over omega, which equals, let's look back, 120 over 4, which equals 30 seconds. Boom, boom. So they're not hard, but they are really uncomfortable, you know. Let's derive some equations from these diagrams. So here's my first equation, and I say, well, look, what I want is at any time, I want to know what this value of x is as this angle changes. Oh, look, this is trig. I would say x is equal to hypotenuse cosine the angle. X is equal to, the hypotenuse happens to be the amplitude, so it's x is equal to a cosine omega t. Provided I moved my mass to the right hand side and let it go when the clock said 0. Okay? Because I'm going, it's important that I go like that. Yeah? So it's a cosine relationship. That's +1, that's -1. So I had to start off when the clock said 0, and I had to move to the right and let it go. And for the most part at the beginning, that's what we're going to do. Okay, so let's do a bit more. So now I know my circular motion has a certain tangential velocity, and if I can find the horizontal component of that, then I will have my my velocity of my oscillator. So I say, well, hold on, if that's omega t, then that means that's omega t, and if that's omega t, then that means that's omega t, and if that's omega t, that's omega t. Okay, so that's omega t, and that's omega t. And if I look at this omega t up here, then this is an opposite. So I can say V is equal to, well, Vt sine omega t, because it's the opposite. It's no longer the cosine, it's the sine of the angle. And why is it negative? Well, that's pointing in a negative direction, so it's minus Vt sine omega t. All right, I don't want to work with 101 different symbols, so I want to convert my Vt into something that I'm familiar with. And I know, remember what we did before on the last page? We said angular, the tangential velocity equals the angular velocity times r. And I know in this case that my r is always the size of my maximum displacement, which is my amplitude. So this equals omega a, substitute in. So I go minus a omega sine omega t. I've got an expression now for the instantaneous velocity of that point. And if I want, I can look at this trig again, and I can say, well, I have this thing called centripetal acceleration, and I have this acceleration, and the angle between them is omega t. So A is equal to minus AC cosine omega t. And I know from previous studies with, remember what we said, AC was equal to V squared over R, which equals omega squared R from physics 1. And I know that R is A, so this is omega squared R rather than AC. Substituted in, and I get minus A omega squared cosine omega t. I just derived by using a bit of trig my displacement in time, my velocity in time, and my acceleration in time of a simple harmonic oscillator. That thing bouncing up and down. I got it. It's really nice. I could have done this by calculus, of course, because if I know that v is equal to dx by dt, I can just differentiate that with respect to time, and I get that. And if I remember that a is equal to dv by dt, I can differentiate that, and I get that. Either way, know them. Either figure them out one way or another, but know them. And what's not so obvious, but you can kind of see, is that, well, there's an A, and there's a cosine, and there's an omega t, and didn't we have that up there? So this says that minus omega squared x, my acceleration at any instant, is equal to minus my angular frequency squared times the displacement. So it's, I think, very powerful, but that's what engineers do. Engineers very often, they'll use diagrams or they'll use calculus, and they'll just go to the next step. So here's an example. Spring and block system oscillates with simple harmonic motion. This is time. You'll see me draw this every time. I am practicing. Block is moved 5 meters. It really should say to the right. Block is moved 5 meters from its equilibrium position. The block is released and the system has an angular frequency, so omega is equal to 2 radians per second. And what is the velocity of the block? So I want my v, don't know what it is, t, delta t, equals 1.7 seconds. Well, if I start my clock at 0 seconds, then this is my t equals 1.7 seconds. Okay. So I've made my list. My equation, that's nudging my memory. X is equal to a cosine omega t. That means that v is equal to, what was it? Minus a omega sine omega t. And then what was acceleration? Acceleration was minus a omega squared cosine omega t. Is that right? Why do I write those 3 down? Because I want to learn them. I want to practice them. I want it so that they're second nature. It's like you got a choice. You might not care what you look like at home. You might only care what you look like when you go out to a party. But if you only ever comb your hair the night you go out to a party, it's going to be really hard on that night. If you comb your hair every day, it gets not only easier, you train your hair so it kind of naturally lies in the right form. It's a bit like that with equations. If you only ever use them in a test, good luck. They'll be like the strangest things you've ever seen. But if you use them and write them down over and over and over again, every time you get the opportunity, write down the equation, whether you're serious about it or not, they'll become second nature. They'll get to the stage where they'll be so much in your long-term memory, you'll never have to worry about them again. And when you get to those upper division courses, you will be unusual in that. Because many of the other places you'll have had equation sheets and they'll walk in not knowing anything. So watch out for that. So, okay, so we got our equation. So we say V is equal to, and minus, and then A. Oh, A is not mentioned here, but do I know A from my visualization?
5 meters.
Yeah, there's my A, isn't it? My A is how far I move it to the right and let it go. So A is equal to 5 meters, so that's going to be 5. And omega, I was given omega. Omega's 2, but I got to square it. And then cosine of 2 times 1.7. So V is going to equal 2 2s are 4, 5 4s are 20, minus 20. Did I do that the right way around? Yeah, minus, no. Yeah, that's right, yeah. And that's a sign. I'm doing the wrong one, aren't I? That's the sign, man. So 5 2s are 10, sine, and that's going to be 3.4. Okay. Piece of cake. I get my handy dandy calculator, which hopefully I brought. In this class, for tests, I give you one of these. It's a classroom set. It's a TI-30X2S. It's not got memory in it, so I don't have to worry about equations being plugged into it. It's not got any equations written on the back, and it's not messed with. Okay. You might want to get one of these just so that you get comfortable with it. It costs like $8 or $10 or something. Notice professional engineering exam. Professional engineering exam, they don't let you bring in your own calculator. They actually have only certain non-memory types of calculators. There's like 2 of them that they allow. So it's not unusual to be restricted. And I've done it for various reasons. So get comfortable with this. If you're in a test and you just can't remember how do I get this from floating point into scientific notation or vice versa, I know that stuff. I can tell you that. I'd like you to know that if you're stuck, I'm not going to say, to heck with you, you know, I'm going to help you. If you can't remember how to change the mode, these are nice because this one actually tells you the mode. This actually tells you the mode. Unlike the TI-83 where it lets you guess, this one tells you the mode you're in. So are you in degrees or radians? What should we be in on this? Should we be in degrees or radians? How do you know? Angular, yeah, omegas and all that kind of stuff. So then I simply turn around and say, okay, put your glasses on. And I'm in degrees, so I go DRG. I click it across to radians, I go enter. I'm in radians, it says, oh yeah, you're in radians. And I go, for this one I can go 10 times sine 33.4, close brackets, enter. And I'm getting minus 2.55. So I come down here and I go, oops, not on there. I go V is equal to minus 2.55. V is equal to plus 2.55. Put it in a box so that even that old fella can see it. I'm almost finished. What's missing? Units, and that matters. Units per second. It's like the difference between $20 notes and $1 notes. You know, big difference between 5 $20 notes and 5 $1 notes. So the units matter. So there we have it. Most common mistake on this would be being in degrees rather than radians. And that matters. It's not the end of the world, but it matters. And also forgetting that sign, not propagating your signs right. Looking at your calculator and just writing down negative. Let's think about me now. I'm your examiner. I'm your coach and your cheerleader most of the time, but on test day, I'm your examiner. And what do you give me? If you just give me a whole bunch, so first of all, how do I grade? I look here, is it the right numerical answer? If it's the right numerical answer, I pull it out, and I look and just check that it makes sense. You didn't just copy from the person next to you, there's actually work that substantiates it, and you get the points. I look and see, is it like a blank, or is it like just a scribble, or is it nonsense, you know? And I take those out, and they're gone. And then I'm left with this group of people who are in between. They have the wrong answer. It looks like they made a serious attempt at it. And I start looking to see, can I give them partial credit? And so first thing I look at and say, is there a diagram? And if there's a diagram, frankly, I got more sympathy. Because at least, you know, when I've been telling you to kind of put your shoulder into the swing, I can see they've been putting their shoulder into the swing. Maybe they didn't do it right, but at least they've been kind of like, you know, taking my advice. And then the second thing I look at is there an equation written down? Because what can happen is, supposing, so think about what I did. I wrote down my 3 equations, and then I was looking at the bottom equation and doing this. And I put the square in, yeah? So I could see, well, that person is thinking about this equation, but they've transcribed the wrong bit. That's not as serious as if you just give me a whole bunch of math with a square in, because then I don't know if you know the equation or not. It's not a mathematical mistake, it's an actual huge mistake. So the more, and then the other thing is, why do I write down all these steps? And I write down all these steps because when I am nervous, I will make slips if I'm doing things in my head. And when am I nervous? Well, I don't do tests. I'm fine with tests. I'm going to be sat there having, sipping my tea and just happy as could be. No, I'm nervous when I'm in front of a class, especially a new class, and I'm doing something on the board. That's when I make more slips. And if I make a lot of slips, then I can see the class's eyes glaze over because they don't feel that I have the right to teach them. So it's a real issue. And I've been there when I first came back to teaching. Man, I was there. So somewhere I had to make a system whereby I made fewer and fewer mistakes, even when I was nervous. And you face the same thing on test day. So you've got to have a system whereby you make fewer and fewer mistakes, even when you're nervous. And my advice, just lay it out, just line after line after line, and you will catch your mistakes. If it's in your head, as soon as you've moved on to the next question, all that work is gone. And, you can't check that. It's done. It's gone. So really, this is not like multiple choice. There's not going to be, I got 27. This one says 25. That's probably the right answer. That's not going to happen. It says 27. You got 25. Man, maybe that's a huge problem. So it's like a presentation type thing. Slow down and show me everything. And I'm going to be the guy that marks it. So show me the kind of style that I show you. Yeah. Oh no, I mean, if you get all the questions right and there is work there, I'm not going to quibble and say, oh man, you're not doing it my way. If it's successful, it's successful. But if it's not successful, I'm going to be on you to do it my way. Because, Oh, so this is a bit of a mess. Occasionally this happens. I'm so sorry. Somehow something happens when I'm going from one to the other. Let's play with this a bit. Natural frequency. Let's try and find the natural frequency of something. Well, I know that A is equal to minus K over M times X. Let's just put that in so we can see that that's the equation. And then we know, well, that AX is equal to minus omega squared X. So K over M equals omega squared. So omega is equal to the square root of K over M. So where did this sorry about that, it's all kind of messed up. And then I said that T, the period, big T is the period, little t is the time. They're not the same thing. Big T is the period. Big T equals 2 pi over omega. So that means that T is equal to 2 pi times the square root of M over K. So you can go two ways on this. You can turn around and say, well, I'm gonna learn this and figure out that, or I can learn that and figure out that, or I can learn them both, or whatever. Some of you will be familiar with T is equal to 2 pi root L over G. Anybody know what that is? Have you seen it before? Did you do pendulums in Physics 1 or Fundamental Physics? Maybe you did. That's the equation for that. Can you see the similarity? For that system, T equals 2 pi root L over G. For this system, T equals 2 pi root M over K. There's an issue here that's confusing. K over M, M over K. It's easy to get that confused. So it's worthwhile double checking by the logic of it. If I increase my mass, I expect my system to be more sluggish. So I expect a longer period. So mass should be on top. If I increase my mass, I expect my system to be sluggish. So the frequency should be less. So M should be on the bottom. So it's logical. It's just that you kind of like, you write down what you think it is, and then you kind of say, have I got it the right way around? It's going to be a square root in either case. How am I doing for time? Not so bad. a spring and block system oscillate with simple harmonic motion. The spring has a spring constant. So here's my spring and block system. This is K is equal to 8 newtons per meter. It oscillates with simple harmonic motion. There's my 5-minute warning. So it oscillates with simple harmonic motion. So here's my time. And 32 grams. I always put my masses in kilograms inside the object. So 32 grams, 32 kilograms. Block is displaced 3 meters. So this is 3 meters. And what is the period? T. So let's make a bit of a list. So I put a box around that. T equals, I don't know. M is equal to 32 kilograms. A is equal to 3 meters. K is equal to 8 newtons per meter. Jog, jog, jog of my memory. T is equal to 2 pi root, square root of, it's going to be M over K. T is equal to 2 pi square root of M, 32, over K, 8. T is equal to 2 pi of root 4. T is equal to 2 pi times 2. T is equal to 4 pi, and it's a time, so it's going to be in seconds. Now, there's my answer, it's there. Couple of things. So I'll give you a second. A couple of things on this. Number one, notice I'll put all the steps down. Number two, I did not use amplitude. Yeah, that's a red herring. That's so that if you're not solid on what your equation you need to use, you'll be going, what equation has an A in it, and these sort of things. So that's quite legitimate. That's a red herring. That's a physics. It's so that we don't just descend into this, let's just put numbers into equations. You have to think about this to some extent in physics terms. Sometimes I'll let you leave letters in, not pi's actually typically, but G's for gravity, mu naughts, and epsilon naughts in electricity and magnetism. There's a tendency for people when they put down a Greek symbol to forget their units. Don't forget your units. I mean, even if you're putting down an epsilon naught, you've got to put your units in. So always double check your units. Make sure you have units. Let's